What happens when the most powerful telescope ever built focuses on the most powerful aurora in the solar system? The James Webb Space Telescope recently captured Jupiter's northern lights in stunning detail, revealing a cosmic mystery that puzzled scientists. Like a detective uncovering unexpected clues, JWST's images show auroras that defy explanation. Jupiter's auroras pump out more energy than should be physically possible, given what we know about aurora formation. They appear in places they shouldn't be, and behave in ways that challenge our current understanding of planetary physics. Today, we're explaining exactly why these beautiful phenomena have become one of space science's most fascinating unsolved mysteries. Earth's aurora versus Jupiter's cosmic light show. To understand why Jupiter's auroras are so puzzling, we must start with our planet's light shows. Here on Earth, auroras form through a relatively straightforward process. When the sun releases energy through solar flares or coronal mass ejections, it races charged particles through space. These particles, primarily electrons and protons, get caught in Earth's magnetic field and are guided toward our poles. As these energetic particles spiral down along magnetic field lines, they collide with gases in our upper atmosphere. These collisions excite oxygen and nitrogen atoms, temporarily boosting their electrons to higher energy levels. When those electrons return to their normal states, they release energy as light, creating the dazzling curtains of color we know as the northern and southern lights. Earth's auroras follow predictable patterns based on atmospheric chemistry. Oxygen produces greens at lower altitudes and reds at higher elevations, while nitrogen contributes blues and purples. Each gas emits light at specific wavelengths, almost like a signature. Think of Earth's auroras as a well-rehearsed symphony, with each atmospheric element playing its designated part at precisely the right moment. Jupiter seemed like an obvious candidate for auroras. With its enormous size and powerful magnetic field, scientists expected Jupiter to display auroras working essentially the same way as Earth's, just on a grander scale. The basic mechanism should be identical. Particles trapped in magnetic fields, exciting atmospheric gases, and producing light. The first hints of Jupiter's auroras came in the 1950s, when radio telescopes detected signals indicating a powerful magnetic field. Confirmation arrived in 1979, when Voyager 1 captured the first images during its flyby, revealing auroras primarily visible in ultraviolet light rather than the visible spectrum we see on Earth. Jupiter's magnetic field is exceptional, roughly 20,000 times more powerful than Earth's. Generated by the planet's rapid rotation and electrical currents flowing through metallic hydrogen in its interior. This magnetic powerhouse creates auroras that dwarf our own. Jupiter's displays reach 1,000 times the energy of Earth's most intense auroras and cover areas larger than our entire planet. Unlike Earth's carefully choreographed light show, Jupiter's cosmic performance follows different rules entirely. A major clue that something unusual was happening came from a simple observation. Jupiter's auroras never stop. While Earth's auroras flare up during solar storms and fade during quiet periods, Jupiter's auroras shine constantly, suggesting something beyond solar activity powers them. This permanent light show was the first sign that Jupiter's auroras operate by different principles. When the James Webb Space Telescope turned its powerful instruments toward Jupiter, it revealed something that has forced scientists to question everything they knew about how auroras work throughout the cosmos. The broadband mystery, what JWST revealed. The James Webb Space Telescope represents a quantum leap in our ability to study distant worlds. Unlike previous instruments, JWST can penetrate cosmic dust and detect infrared light with unprecedented sensitivity. When scientists aimed this remarkable tool at Jupiter, they expected to finally see the planet's auroras in extraordinary detail, confirming what decades of theory had established about how these phenomena work throughout the solar system. Based on everything we understand about aurora formation, Jupiter's light shows should produce what scientists call discrete emissions. Think of discrete emissions as very specific fingerprints of light. When charged particles hit oxygen in Earth's atmosphere, they produce precise wavelengths, specific colors of light that correspond exactly to the atmospheric gas being excited. This creates the distinct green and red hues in our northern lights. Each gas has its own emission pattern, its own unique light signature that scientists can identify. Yet what the JWST revealed challenged every preconceived notion, as if the rules of light were being rewritten. When data started coming in, scientists noticed something was immediately wrong. Jupiter's auroras didn't show the expected discrete emission patterns. Instead of producing light at specific wavelengths, Jupiter's auroras were emitting across a continuous spectrum of energies. This broadband emission pattern defies our conventional understanding of auroras. Like seeing a smudged watercolor painting where we expected a crisp barcode of distinct lines. The JWST observations revealed another puzzling detail. The brightest areas of Jupiter's auroras in infrared wavelengths didn't match what the Hubble Space Telescope had captured in ultraviolet light. We were seeing completely different energy distributions than expected, noted lead researcher James O'Donoghue. This discrepancy points to a mysterious energy transfer mechanism scientists can't fully explain. Even the location of Jupiter's auroras defies expectations. On Earth, auroras form in an oval pattern around the magnetic poles. Jupiter's auroras appear in unexpected regions that don't align with current magnetic field models. Some of the brightest emissions occur in places where they simply shouldn't exist, according to our understanding. Adding to this cosmic puzzle is the influence of Jupiter's volcanic moon, Io. This moon constantly ejects material into space through its active volcanoes. These particles get caught in Jupiter's magnetic field, creating their distinct aurora footprint in Jupiter's atmosphere. Perhaps most surprising is the evidence that Jupiter is actively generating much of the energy for its auroras. The constant nature of Jupiter's auroras, combined with their unusual energy signatures, suggests the gas giant is converting its immense rotational energy into electrical currents that power these light displays, essentially creating its internal aurora generator. These revelations from JWST have transformed Jupiter's auroras from a scaled-up version of Earth's familiar phenomenon into one of the solar system's most perplexing mysteries, forcing scientists back to their theoretical drawing boards. The plasma puzzle, current theories, and unanswered questions. So, what could explain these bizarre auroras that seem to break the rules of physics? Scientists now believe the key might lie in Jupiter's unique atmospheric composition. While Earth's upper atmosphere consists of complete atoms with their electrons intact, Jupiter possesses what scientists call a plasma layer, the fourth state of matter, where electrons and positive ions exist separately. This plasma environment fundamentally changes how energy moves through Jupiter's upper atmosphere. On Earth, auroras occur when charged particles hit complete gas molecules. On Jupiter, these interactions happen within an already energized plasma environment, creating entirely different energy pathways. Jupiter's rapid rotation adds another crucial element. The gas giant completes a full rotation in under 10 hours, generating powerful electrical currents flowing through its atmosphere. Unlike Earth's occasional displays, these currents provide the constant energy source that keeps Jupiter's auroras perpetually active. The turbulence created by this spinning magnetic environment traps charged particles within Jupiter's upper atmosphere. These particles become caught in complex magnetic field lines, bounce between the poles, and interact with the surrounding plasma, creating continuous energy emissions rather than discrete patterns. One promising explanation involves wave acceleration. As Jupiter rotates, it creates waves in its magnetic field, ripples spreading through the plasma environment. Charged particles surf these magnetic waves, gaining tremendous energy. Scientists studying Juno's data describe this phenomenon as tiny electrically charged surfers riding waves of energy through Jupiter's atmosphere. This surfing mechanism could explain the broadband energy signature that JWST observed. Instead of particles creating discrete wavelengths, we see particles accelerated to various energy levels by magnetic waves, creating emissions across a broad spectrum. Several observations remain puzzling. The electrons causing Jupiter's auroras sometimes reach energies as high as 400,000 volts, far more than expected. Other times, they operate at much lower energies or fire in seemingly random directions that don't align with magnetic field models. NASA's Juno mission has been collecting data since 2016. It follows a polar orbit that passes directly over Jupiter's auroras every 53 days. Despite these efforts, much remains unknown about the fundamental processes driving these auroral displays. The challenges are extraordinary. Jupiter's radiation environment is so intense that it damages spacecraft instruments. Even Juno, specifically hardened against radiation, can only survive limited exposure to the most intense radiation belts. The energy source might originate deep within Jupiter, connected to the planet's radiation belts or internal dynamics. These findings could revolutionize our understanding of planetary magnetospheres throughout the universe. After decades of observation, Jupiter's auroras remain one of planetary science's most fascinating mysteries. They challenge our understanding of how planets interact with their space environments, and remind us that even in our cosmic neighborhood, nature still holds profound secrets. Jupiter's auroras reveal how little we truly understand about planetary physics. These cosmic puzzles force us to reconsider our models of magnetic field interactions throughout the solar system. What we learn from Jupiter could redefine our approach to studying distant exoplanets and their potential for hosting life. The upcoming Europa Clipper mission, which will reach Jupiter by 2030, will carry instruments specifically designed to study these aurora interactions. Jupiter's proximity may finally unlock the mechanisms behind these mysterious energy patterns. In the grand tapestry of the cosmos, Jupiter's glowing lights remind us that even with our most sophisticated technology, the universe still holds profound secrets waiting for discovery. If you're as fascinated by space as we are, you won't want to miss these other videos. We dive even deeper into the universe's secrets and explore recent discoveries that could revolutionize your understanding of the cosmos. Thank you for joining us on this cosmic adventure. Stay curious and keep looking up.